So, welcome to the second class of Computing Fundamentals, and today we will discuss sets, and then we will speak about functions, sequences, and sum and matrices. And in this chapter, we will focus more about the language of set. Today, specifically in this class, we will speak about sets and their operation and their identity. Then, by the coming weeks, we'll discuss functions and sequences and summarization. So, we will focus about how we define a set in math and then how we can describe them based on a mathematical quantifier. And then we will discover or recall some important sets that we know from the time we were in school. Then we will discuss what we mean by empty set and universal sets. Then we will study the cardinality of sets, and then the Cartesian product of sets. So first, what we mean by sets. They are one of the basic building blocks for discrete mathematics, and they are very important in computer science because a database, any table in the database is basically a set. Any Python list is a set. Do you know Python list? It is a set. Now, you can extend this further and you say any Python dictionary is as well a set. And they are very important for a programming language, and the set operation, we always use set operation to find out, for example, how many students score more than 90 in Computing Fundamentals 1. Because basically you do a join between two tables, and this join is basically an intersection between two sets. Now, set theory is a very important branch of mathematics, and many different systems have used sets to define the relationship between different entities, elements, and objects. So a set is an ordered collection of objects. And objects could be anything. Now, this could be the students in this class. It also could be the chairs in the room. Now, the objects in the set are called the elements or the members of the set. And normally, the relationship between the set and its members, it's basically containing. So a set contains those members. Now, the notion where we have the small e, normally a small a, the character small a, belongs to the capital A, denotes that this element, this small element a, is basically an element of the set capital A. So if A is not a member of capital A, we write it basically A not belongs to A. It's not an element of A. So how you would describe a set? You can use this notation for describing the set S, where it's equal, and then you donate in the set all the members inside it. So A, B, C, D, all are elements of the big set S. Now, in set theory, in the order of those elements, how they appear in the set representation is not important. Because basically the above set S, where A comes first, is similarly equal to B, C, A, and D. And this is what we call equality relationship, which I don't believe it's a true equality, because this is basically a similarity. Because you are talking about a set with the same elements that is similar in the structure with another set with the same element. And we will discuss this in details in the coming few slides. Now, in the set, each distinct object is either a member or not. So you always have like a list of all the members in the set, and you donate them by this notation. So you sometimes use the ellipses instead, or the parentheses, so you have all the members when the pattern is clear. The relationship between those elements is clear. Like this set contains all students in age between 20 to 25. This is what we mean by the relationship. So it will appear like you know the rest of it, like etc., etc., etc. So you know the rest of the set, which one should be a member or not a member of the set. Now, example of sets, like let's say the set of vowels in English. V, capital V, equals to A, E, I, O, and U. Now, the set of all positive integers less than 10. Now here I define the relationship between the numbers less than 10. So basically we have 1, which is an odd positive integer. This is like the relationship between the elements in the set. Now 3 is as well an odd positive integer, and it's also less than number 10. Now take, for example, the set of all positive integer less than 100. Basically here I know that 1 is a positive integer less than 100. 2 is as well a positive integer less than 100. 3, etc., etc., up to 99. And this is where you can use the ellipses, just the dots, to explain that the relationship between those elements is going to be the same. So we are talking here about a set where all elements have a homogeneous relationship. So the elements are homogeneous. Normally we call them homogeneous because there is a mathematical relationship between them. Now if they have, sometimes you have a set with elements which are heterogeneous, which means they are like distributed. There is no relationship between them, but they come to happen in the same set. Another example, you can say the set of all integer less than 0. So S, for example, including -3, -2, -1. Now everything before those numbers is given by the relationship I just defined. Now some important sets that you need to recall and remember for this class. The capital N, which is basically stand for natural numbers, where we start with 0. By the way, we call them natural because we find them in nature. You can find 1 tree, 0 tree, 1 tomato, 0 tomato, and so on. So you can measure them in nature. But you have the other set, which is capital Z, which denotes all integers numbers, including positive and negative values. And it's also including 0. By the way, 0 was an invention. It was like something they discovered later on, like many years after inventing the set theory. Now when you speak about Z positive, Z plus, capital Z plus, this stands for positive integer not including the 0. Now R is the set of real numbers where we have a fraction, 1.5, 2.5, and so on. Now R plus is the positive real number because the previous one contains -2.5, -0.5, and so on. Now C and Q are a set of complex number. Complex number is the number where you can obtain by the notation A plus B multiplied by I, where I is a real number. We don't really worry now how a complex number obtained, but this is how we call the set of complex number. And also we have capital Q, which stands for rational number. Now the easiest way to remember all of these type of sets is just to draw them in the notation you see here in the slide, where we have a small n. Now look, Z is containing all the big set of n is contained in the set Z capital. The set Q, for example, the set of rational number, contain everything, including integers, including positive integers, including as well complex number, and R as well is a set of real numbers which contains every other set in those examples. Now how you can build or define a set? Let me give you some examples. So you normally specify the relationship between the elements of the set using a quantifier. So if you want to describe a positive integer less than 100, you can use the quantifier relationship where you say the set as capital equals to x, where x is positive integer less than 100. So this is the relationship. So anything which satisfy this rule would be an element of this set S. Now the set O is basically has an element called x, where x is an odd positive integer less than 10. So any number positive and odd is an element of the set O. So this is including 3, 5, 7, 1, 9. But it will not include, for example, -1 or -3, because I define the relationship to be a positive odd integer. It will never contain any real number as well. You can also include everything in the big set like Z plus, where you say O is a set where x belongs to the Z capital plus, all positive integers. So x is an odd and x should be less than 10. This is like you refine it, like you refine the generic definition. You don't take all numbers in Z plus and you define them by a specific relationship. So a predicate could be used to describe the element of the set as well, based on the notation a set like S capital has an element which is x, and this x could be defined by the function p of x. Now you can define this function further and you say, for example, the positive rational number q plus is a set. I have element in this set called x, and this x belongs to the set capital R, which is real numbers, positive and negative, where we have x as well equals to p divided by q. Now p and q as well positive integer. So I am exactly specifying which one should be qualified to be in this set. So the interval notation, you could also use interval, okay, with the square brackets, just to explain the elements of the set instead of quantifier. You could say, for example, there is a set has an element A and B, and this set could be defined. Those elements in the set could be described using this mathematical notation. X is the element in the set, and this X is basically greater than the value of A, less than or equal the value of B. So this set is including an interval. So, for example, this set contains all the elements from 2 to 5. So this means 3 is greater than or equal 2 and less than or equal 5. So it should be an element in this set. So any notation or any of these symbols could be used, whether you close the parentheses, which means it's a closed set, it's not an interval, or you make a square bracket to denote that this is an interval. It's not the complete set. It's a range of value, okay? It's a range of value. So normally a closed interval will be with the square brackets and open interval will be with parentheses. Now the easiest notation that we could use to simplify or to present sets, we call it the Venn diagram. Now how we can speak about this? Now imagine that there is like universal set called U capital, which contains every atom in the universe. It will contain everything you could believe or think about. This is like the largest set you could ever think about. It will have real numbers, integers, stars, galaxies, whatever you think is there in this big set. Chairs, students, cars, anything. So anything you could consider or you could measure in math could be an element in this big U. Now there is as well another set called phi, or the empty set, because there is no element in it. And we normally use the phi character to denote an empty set. So if you look to the Venn diagram, this is how you represent, for example, the set of U, which is basically everything available under consideration. And this is like the big V capital, the small set which contains the vowel characters in English. And it will contain like a small portion of it. So this is how you would represent it. So for example, let S capital be the set of all sets which are not members of themselves. Okay? Now, the result from trying to answer this question is S capital a member of itself. Now, you can rephrase this question by saying Henry is a barber and who shaves all people who do not shave themselves. Now the result from trying to answer this question, does Henry shave himself? So this would answer the question that basically the set S could be a member of itself. But by the definition, S is a set of all sets which are not member of themselves. So by definition, this S is not member of itself. Okay? So by definition, S is not a member of itself. So a set can be elements of another set. So for example, the set 1, 2, 3 is an element of another larger set where it is also an element with A and another small subset called B and C. And then you have another set called N capital Z, capital Q capital and R capital, which is, you can call it W. Now the empty set is different from any other set because it's containing the empty set phi. And phi is also an element of every other set exists.